Welcome to today's problem walkthrough. We're tackling a classic algorithmic challenge, problem number 279, titled Perfect Squares. This problem explores the concept of finding the least number of perfect squares that sum to a given number. Let's dive in and break it down step by step. In this problem, we are tasked with finding the least number of perfect square numbers that sum up to a given integer, n. A perfect square is any number that can be expressed as the square of an integer. For example, 1 is a perfect square because it is 1 caret 2, 4 is a perfect square because it is 2 caret 2, and so on. Common examples of perfect squares include 1, 4, 9, 16, and so forth. The input to this problem is a single integer, n, where the constraints ensure that n is at least 1 and at most 10,000. The output is another integer that represents the minimum number of perfect square terms needed to sum up to n. Let's look at a few examples to better understand what this means in practice. For instance, if n is 12, we are asked to determine the smallest number of perfect squares that, when added together, equal 12. The output for n equals 12 is 3. This is because the number 12 can be expressed as the sum of 3 perfect squares, 4 plus 4 plus 4, which are all 2 caret 2. Importantly, there is no way to represent 12 using fewer than 3 perfect squares, so the answer is 3. Now, consider another example where n equals 13. In this case, the output is 2 because 13 can be written as the sum of 2 perfect squares, 4 plus 9, which correspond to 2 caret 2 plus 3 caret 2. Again, this is the smallest possible number of terms needed to achieve the sum of 13. Looking at yet another example, if n is 1, then the output is simply 1. This is because 1 is itself a perfect square, specifically 1 caret 2. Therefore, the least number of perfect squares that sum to it is just 1. These examples highlight the core goal of the problem, to find the minimum number of perfect square terms that add up to the given number. Whether the input is a single perfect square, like 1, or a combination of multiple squares, like in the case of 12 or 13, the solution must always ensure the count is minimized. Now, let's summarize the constraints and edge cases we need to consider. The input number n will always be between 1 and 10,000, inclusive. For the smallest input, such as n equals 1, the output is straightforward, as 1 is already a perfect square. For larger values, like n equals 10,000, the solution must be efficient to handle the computation within the given limits. Additionally, if n happens to be a perfect square itself, such as n equals 4 or n equals 9, the output should be 1 since the number can be represented by a single term. Finally, for non-perfect square numbers, like 12 or 13, the solution must correctly determine the minimum number of terms required. This ensures accuracy across all possible cases, from the smallest to the largest values of n. To solve the problem of finding the least number of perfect squares summing to a given number n, one approach we can consider is a brute force solution using recursive backtracking. The idea here is to start with the number n and recursively subtract perfect squares, such as 1, 4, 9, and so on, from it. At each step, we explore all possible perfect square values that are less than or equal to n, and for each recursive path, we keep track of the count of perfect squares used. By the end of this process, we return the minimum count across all paths. However, this approach has significant drawbacks. Its time complexity is exponential, as each recursive call branches out into multiple subproblems, leading to redundant computations. Additionally, the recursion stack can become deep, consuming n space. While the brute force approach is conceptually simple, it is highly inefficient for larger values of n and doesn't take advantage of overlapping subproblems, which is a key opportunity for optimization. A more efficient strategy is to use dynamic programming with a bottom-up approach. The intuition here is to avoid solving the same subproblem multiple times by storing solutions to smaller subproblems in a DP table. We define dp, I, as the least number of perfect squares that sum to I. To build this table, we start with the base case dp, 0, equals 0, since 0 perfect squares are needed to sum to 0. From there, for each number I from 1 to n, we calculate dp, I, by iterating through all perfect squares less than or equal to I. For each perfect square, we determine the minimum value of dp, I x, plus 1, where x is the perfect square. This ensures that we are building our solution iteratively and efficiently. The dynamic programming approach has a time complexity of O, n asterisk sqrt, n, as for each value of I, we iterate through approximately sqrt, I, perfect squares. It requires O, n, space for the dp table, making it much more efficient than brute force. While it avoids redundant computations, it does involve iterating through all smaller perfect squares for every I, which can become computationally intensive for very large n. Finally, there is a mathematical approach based on Lagrange's first-square theorem, which states that any positive integer can be expressed as the sum of at most 4 perfect squares. This allows us to use a more theoretical framework to solve the problem. First, we check if n is itself a perfect square, which would immediately solve the problem. If not, we test whether n can be expressed as the sum of 2 or 3 perfect squares using mathematical properties. If neither of these cases applies, we can safely return 4, as the theorem guarantees that no more than 4 perfect squares are needed. This approach is highly optimized, with a time complexity of O, sqrt, n, for checking sums of squares, and it uses constant space since no additional memory structures are required. However, implementing this method requires a deeper understanding of number theory, which can make it less intuitive and practical for competitive programming. For this reason, we chose the dynamic programming approach as the most balanced strategy. It is straightforward to implement, avoids redundant calculations, and is efficient enough for typical problem constraints. While Lagrange's theorem provides a faster theoretical solution, the DP approach offers a more accessible and practical method for solving this problem in real-world scenarios. The perfect squares problem asks us to find the minimum number of perfect square numbers that sum up to a given positive integer, n. Perfect squares are numbers like 1, 4, 9, and so on. For instance, if n is 12, the result would be 3, because 12 can be expressed as the sum of 3 4s, which are perfect squares. To solve this, one approach we can use is recursive backtracking. The key intuition here is to recursively explore all possible combinations of perfect squares that add up to n. At each step, we reduce the problem size by subtracting a perfect square from n and solving the smaller subproblem. The goal is to find the combination with the smallest number of perfect squares. To implement this, we define a recursive function, findMinsquares n, which returns the minimum count of perfect squares needed to sum up to n. The base case is straightforward: if n is 0, no numbers are needed, so we return 0. Then, for each perfect square that is less than or equal to n, we subtract that square from n and recursively solve for the resulting value. This forms the foundation of the brute force approach. To refine our recursive solution, we introduce the concept of tracking the minimum count of perfect squares across all valid combinations. We use a variable, minCount, initialized to infinity, to keep track of the smallest result encountered. For each recursive call, we update minCount with the smaller value between the current minCount and 1 plus the result of solving the subproblem. This ensures that we always retain the optimal solution as we explore different paths. Once all valid perfect squares have been considered, we return minCount as the result. Additionally, we need to handle edge cases carefully. For example, if n itself is a perfect square, the answer is simply 1, because we don't need any additional numbers. Likewise, for small values of n, such as 1, 2, or 3, we must ensure that our logic correctly computes the result without errors. These steps complete our brute force approach, though its efficiency can be improved further. The brute force approach, while conceptually simple, comes with significant challenges. First, it relies on recursive exploration, which means it examines all possible combinations of perfect squares that sum to n. This guarantees correctness but leads to exponential growth in the number of recursive calls. The resulting recursion tree is vast, making the approach computationally expensive. Another issue is redundant calculations. For example, the subproblem findMinsquares, 12, might be solved multiple times within the same recursion tree, wasting computational resources. These inefficiencies highlight the need for optimization. One promising avenue is to use dynamic programming. By storing the results of already solved subproblems, we can avoid recomputing them and drastically reduce the time complexity. This optimization not only eliminates redundant work but also makes the solution scalable to larger values of n. To optimize the brute force approach, we need to leverage appropriate data structures. The recursive solution inherently uses the call stack to manage intermediate states, but this can lead to stack overflow if n is large. To address this, we can introduce a memoization table, such as a dictionary or an array, to store the results of subproblems. Each time we solve a subproblem, we save its result in the table, so future calls can simply retrieve the stored value instead of recalculating it. This optimization is key to improving the algorithm's efficiency. Additionally, generating the list of perfect squares less than or equal to n is an important step. Since the number of perfect squares is proportional to the square root of n, this operation is efficient and manageable. Finally, each recursive call reduces n by a perfect square, progressively breaking the problem into smaller and smaller subproblems, making the recursion more structured and easier to optimize. The process of updating the minimum count ensures that the algorithm always returns the optimal solution. By comparing all possible recursive paths, we systematically identify the one that requires the fewest perfect squares. To further optimize the solution, we can replace recursion with a dynamic programming approach. This involves storing the results of find min squares, x, for all x less than or equal to n in a table. With this table, we can compute each result in a bottom-up manner, avoiding recursion altogether. Another alternative is to use breadth-first search, or BFS. Unlike recursion, BFS explores all states level by level, ensuring that the first solution found is the one with the minimum count. This is particularly advantageous because it avoids the overhead of maintaining a recursive stack. In terms of complexity, the brute force approach has a time complexity of 2 to the power of n, in the worst case, due to the exponential branching. However, with dynamic programming, the time complexity is significantly reduced. The space complexity is n for the recursion stack, plus sqrt n for generating perfect squares. To better understand the algorithm, let's walk through some examples. For n equal to 12, we first generate the perfect squares less than or equal to 12, which are 1, 4, and 9. Then, we explore recursive calls by subtracting each perfect square from 12. Subtracting 1 gives find min squares, 11, subtracting 4 gives find min squares, 8, and subtracting 9 gives find min squares, 3. We continue this process until we reach the base case, where n equals 0. At each step, we track the minimum count of perfect squares needed. The result for n equal to 12 is 3, as 12 can be expressed as 4 plus 4 plus 4. For n equal to 13, the perfect squares are the same, 1, 4, and 9, subtracting 1 gives find min squares, 12, subtracting 4 gives find min squares, 9, and subtracting 9 gives find min squares, 4. Again, we track the minimum count at each step. The result for n equal to 13 is 2, as 13 can be expressed as 9 plus 4. These examples illustrate how the recursive process works and how the algorithm arrives at the optimal solution. Here, we start by importing the deque module from the collections library, which will help us implement a breadth-first search or BFS. Inside the solution class, we define the function number squares, which takes an integer n as its input. The first step is to generate all the perfect squares less than or equal to n. We initialize an empty list called squares and use a while loop to compute the square of each integer starting from 1, adding it to the list until the square exceeds n. This gives us all the possible perfect squares that we can use in our solution. Next, we set up the BFS. We initialize a queue using deque, starting with a tuple containing the original number n and a count of 0, which represents the number of perfect squares used so far. We also create a visited set to track numbers we've already processed, so we don't revisit them unnecessarily. The while loop processes elements in the queue, and for each iteration, we dequeue the first element and unpack it into remainder and count. The remainder represents the number we still need to break down, and the count tracks how many perfect squares we've used so far. Then, for each square in our squares list, we calculate the next underscore remainder by subtracting the square from the current remainder. If next underscore remainder becomes negative, we break out of the loop early since the remaining squares will only be larger. Finally, if next underscore remainder equals 0, it means we've found the solution, and we can return count plus 1, indicating the minimum number of perfect squares needed to sum up to n. If the next underscore remainder is greater than 0 but hasn't been visited yet, we add it to the visited set to mark it as processed. We then append a new tuple to the queue with this next underscore remainder and increment the count by 1, reflecting the addition of another perfect square. This ensures that the BFS continues exploring all possible combinations of perfect squares while avoiding redundant calculations. Once the queue is exhausted, if no solution is found, we return the original number n as a fallback. However, for valid inputs, this fallback should never be reached because the problem guarantees that a solution exists. This BFS approach ensures that we explore the shortest path to reduce n to 0, providing the optimal solution in terms of the minimum number of perfect squares. Here, we're implementing a solution to find the minimum number of perfect square numbers that sum up to a given integer n. First, we generate all the perfect squares less than or equal to n. We use a list called squares, and inside a while loop, we calculate the squares of integers starting from 1 and add them to this list until the square exceeds n. Next, we use the breadth-first search (BFS) algorithm to explore possible combinations of these squares. For BFS, we initialize a queue where each element is an array containing two values, the remaining sum and the count of squares used so far. Initially, we start with the full value of n and a count of 0. We also use a visited set to track numbers we've already processed, ensuring we don't revisit the same state and avoid unnecessary calculations. As long as the queue isn't empty, we process each state by retrieving it from the queue, extracting the remaining sum and the count of squares used so far. For each state, we iterate over the list of perfect squares. If subtracting a square from the current remainder results in a negative number, we break out of the loop because the squares are sorted, and all subsequent squares will also be too large. If the remainder becomes 0 after subtracting a square, it means we've found a solution, so we return the count plus 1, as we used one more square. Otherwise, if the new remainder hasn't been visited yet, we add it to the visited set and enqueue it with the updated count of squares used. This process ensures we explore all possible combinations while avoiding redundant calculations. If the queue is exhausted without finding a solution, we return n, although this scenario shouldn't occur for valid inputs since every number can be represented as a sum of perfect squares. This completes the BFS-based approach to solving the problem. To solve this problem for an input of n equals 12, we want to find the minimum number of perfect squares that add up to 12. The perfect squares less than or equal to 12 are 1, 4, 9. We approach this using breadth-first search, or BFS, to ensure that we find the shortest path to the solution. First, we initialize our variables. We set squares to 1, 4, 9, since these are the perfect squares we'll be working with. We create a queue and start by adding the pair 12, 0 to it. Here, 12 is the remaining sum, and 0 is the count of squares used so far. We also define a visited set to keep track of the remainders we've already processed, which prevents unnecessary revisits and improves efficiency. In the first iteration, we dequeue 12, 0, and consider each perfect square. Subtracting 1 gives us 11, so we add 11, 1 to the queue and mark 11 is visited. Similarly, subtracting 4 gives 8, so we add 8, 1 to the queue and mark 8 is visited. Finally, subtracting 9 gives 3, and we add 3, 1 to the queue while marking 3 is visited. This completes the first iteration, and we now have 3 new states to explore in the queue. In the second iteration, we dequeue the next state, which is 11, 1. Here, the remaining sum is 11, and we've used one square so far. Again, we check each perfect square. Subtracting 1 results in 10, so we add 10, 2 to the queue and mark 10 as visited. Then, subtracting 4 gives 7, so we add 7, 2 to the queue and mark 7 as visited. Finally, subtracting 9 gives 2, so we add 2, 2 to the queue and mark 2 as visited. Next, we process other states in the queue, such as 8, 1, and 3, 1. Eventually, we reach a state 4, 2. Subtracting 4 from the remaining sum of 4 gives 0, and since we've reached 0, we stop the BFS here. The total count of squares used is 2 plus 1 equals 3. Thus, the minimum number of perfect squares that sum to 12 is 3, and the squares are 4 plus 4 plus 4. Now, let's solve another example where n equals 13. We aim to find the minimum number of perfect squares that sum to 13. The perfect squares less than or equal to 13 are 1, 4, 9. As before, we initialize our variables. The squares list is 1, 4, 9, and the queue starts with 13, 0, where 13 is the remaining sum, and 0 is the count of squares used so far. The visited set is empty initially. In the first iteration, we dequeue 13, 0, and check each perfect square. Subtracting 1 results in 12, so we add 12, 1 to the queue. Subtracting 4 results in 9, so we add 9, 1 to the queue. Finally, subtracting 9 results in 4, and we add 4, 1 to the queue. At this stage, our queue contains 3 states, 12, 1, 9, 1, and 4, 1. Next, we process the queue further. Dequeuing 12, 1 involves exploring its remainders, which is similar to our earlier example with n equals 12. Then, we dequeue 9, 1, and check its remainders. Subtracting 1 results in 8, subtracting 4 results in 5, and subtracting 9 results in 0. Since we've reached a remainder of 0, we stop here. The total count of squares used in this path is 1 plus 1 equals 2. Therefore, the minimum number of perfect squares that sum to 13 is 2, and the squares are 9 plus 4. For a simpler example, consider the input n equals 1. Here, the only perfect square less than or equal to 1 is 1. We initialize the queue with 1, 0, and an empty visited set. For n equals 1, we start by dequeuing 1, 0. Subtracting 1 from the remaining sum of 1 results in 0. Since we've reached 0, we stop and return the count of squares used, which is 0 plus 1 equals 1. Thus, the minimum number of perfect squares that sum to 1 is 1, and the square is simply 1. From these examples, we can make some key observations about the algorithm. First, BFS guarantees the shortest path, ensuring that we find the minimum number of squares. Second, the visited set prevents us from revisiting the same remainder, which avoids redundant calculations and keeps the algorithm efficient. Finally, as soon as we reach a remainder of 0 in any branch, we stop immediately, ensuring we don't waste time exploring unnecessary paths. This approach ensures both correctness and efficiency in solving the problem. In this problem, we use the breadth-first search algorithm to determine the minimum number of perfect squares that sum up to the given number, n. To begin, we generate all the perfect squares less than or equal to n. This process involves iterating through integers, squaring each one, and stopping when the square exceeds n. Since the number of perfect squares is roughly the square root of n, this step takes sqrt n time. Now, the core of the algorithm is the BFS traversal, where we explore all possible ways to reduce n to 0 by subtracting perfect squares. Each state in the BFS queue represents a remainder and the count of squares used so far. The number of unique remainder values we might encounter is at most n, and for each remainder, we try subtracting all possible perfect squares, which is sqrt n per state. Therefore, in the worst case, the BFS traversal takes n asterisk sqrt n time, giving us the overall time complexity of n asterisk sqrt n. Now let's analyze the space complexity of this algorithm. First, we need to store the list of perfect squares less than or equal to n, which requires sqrt n space. Then, there's the visited set, which keeps track of all the unique remainders encountered during the BFS traversal. In the worst case, this set may grow to contain all numbers from 0 to n, so it uses n space. Lastly, the BFS queue needs to store the states, which include the current remainder and the count of squares used. Since the number of unique remainders is at most n, the queue also requires n space in the worst case. Combining these, the overall space complexity is n. Let's consider the best, average, and worst cases for the algorithm. In the best case scenario, n is already a perfect square. Here, we only need to generate the list of perfect squares, which takes sqrt n time, and BFS terminates immediately. For the average case, BFS typically explores fewer than n remainders, but the worst case time complexity of n asterisk sqrt n still applies. The worst case occurs when all n remainders are visited, requiring the full n asterisk sqrt n time complexity. Comparing this to a brute force approach, where we recursively try all combinations of perfect squares, the optimized BFS is far more efficient. The brute force method has exponential time complexity, 2 to the power of n, because each number has two choices either to be included or excluded. BFS, on the other hand, avoids redundant computations through its visited set, reducing the complexity significantly to O, and *SQRT, n. Finally, let's solidify the time and space complexity with a mathematical proof. The BFS algorithm explores all possible states, and there are at most n unique remainders that can be visited. Each state involves processing all perfect squares less than or equal to n, which is approximately O, SQRT, n, operations per state. Multiplying these, we arrive at O, n *SQRT, n, as the total number of operations in the worst case. For space, the two dominant factors are the visited set and the BFS queue. Both store up to n unique remainders, giving a space complexity of O, n. This analysis confirms that the algorithm is both time and space efficient compared to brute force approaches, making it well suited for this problem. When solving the perfect squares problem, there are several common pitfalls to avoid. One of the most frequent mistakes is not considering all possible perfect squares less than or equal to n. For instance, if you repeatedly subtract the largest square, you may miss the optimal solution. Take n equals 12 as an example. Subtracting 9 first leaves 3, which requires 3 additional steps to reach 0. However, the optimal solution is 4 plus 4 plus 4, which achieves the same result in just 3 steps. Another mistake is relying on inefficient recursion without memoization. This can lead to redundant computations and significantly higher time complexity, especially for larger values of n. Lastly, overlooking edge cases like n equals 0 or n equals 1 can lead to incorrect results or runtime errors. For example, n equals 0 should return 0, and n equals 1 should return 1, which are critical cases to handle properly. Now, another common source of confusion is mistaking depth-first search, or DFS, for breadth-first search, or BFS. While DFS explores deeper paths first, making it inefficient for finding the shortest path, BFS is ideal in this context as it guarantees the shortest path. It's also essential to analyze the time complexity of your solution. Assuming that a brute force recursive approach will work for large inputs is a mistake, as such approaches can lead to exponential time complexity, making them infeasible for constraints up to n equals 10,000. From an interview perspective, it's helpful to highlight that this problem can be thought of as a shortest path problem in an unweighted graph. Each number represents a node, and edges connect nodes differing by a perfect square. This insight naturally points toward BFS as a solution. Additionally, showcasing an understanding of dynamic programming versus BFS and how memoization or pre-computing perfect squares improves efficiency can demonstrate depth of knowledge. Always remember to clarify edge cases and input constraints with your interviewer to avoid surprises. This problem also shares connections with several other problems, which can provide useful context. Examples include LeetCode 322, coin change, where you determine the minimum number of coins needed to make a certain amount, and LeetCode 127, word ladder, which also involves finding the shortest transformation sequence. Other related problems include LeetCode 139, word break, and of course, LeetCode 279, perfect squares. When considering alternative approaches, one effective method is dynamic programming. In this bottom-up approach, we define dp, I, as the minimum number of perfect squares that sum to I. We calculate dp, I, iteratively, using the relation dp, I, equals min, dp, I square, plus 1, for all perfect squares less than or equal to I. This approach has a time complexity of O, n *SQRT, n, and a space complexity of O, n. While it works well for dense inputs, a trade-off is that it consumes more memory compared to BFS. Another viable approach is BFS, which treats each number as a node and generates neighbors by subtracting perfect squares. BFS explores these neighbors level by level, ensuring the shortest path is found. Its time complexity is also O, n *SQRT, n, with a space complexity of O, n, due to the queue. While BFS avoids building a large DP array, managing the queue for larger inputs may require careful handling. Finally, there's a mathematical approach based on Lagrange's four-square theorem, which states that every number can be expressed as the sum of at most 4 squares. While this is an elegant solution and can determine the result directly, it's non-constructive and less practical for coding interviews, where providing a clear implementation is often required. Each of these methods has its strengths and trade-offs, and understanding them equips you to choose the best approach for the situation at hand. Great job following along. In summary, we explored how to solve the perfect squares problem using recursive backtracking. Key takeaways include the importance of understanding perfect squares and the versatility of recursive techniques. Don't forget to practice similar problems and incorporate optimizations like dynamic programming. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!